So, universal gravitation looked like this. Fg equals gmm over r squared. And it also equaled, at or near the surface of Earth, mg. Now, to help explain how two bodies that are not in contact can exert a force on one another, which in physics is weird. Generally speaking, forces require some form of obvious interaction. You have to interact with something. And so to be able to explain what is actually going on, physicists determined this idea of fields. Now, examples of these are, well, the gravitational field or electrostatic field, the magnetic field. Some of them that you've played with. I'm hoping you've had a chance to experience magnetism, for example, as a child. And it's this, at least when physics was first becoming a discipline, this kind of spooky action at a distance, which for a long time made people, physicists, really quite uncomfortable. You can't have action at a distance without something interacting with something else. And so what was done, or what was conceived, I guess, conceptually, is this idea that there are objects out there that have properties that extend beyond themselves. Gravity being one of them. For an object that has the sufficient mass, there is a, well, depending on how you look at it, I'm going to show you a video today, depending on how you understand physics, whether it's Newtonian or Einsteinian, objects in a Newtonian sense, objects that have mass create this field around them that other objects can then interact with. We call that field a gravitational field. It's why Isaac Newton determined that, this is the reason that Isaac Newton says, well, things fall towards the Earth. There's a field that they're interacting with. That field causes them to get pulled in. Same thing with electrostatics. In grade 9, you were part of the curriculum is you play with static electricity, and the idea that a positive charge and a negative charge attract each other. There's fields between, each one of those has a field, and those two fields interact with each other such that those two objects are drawn together. Magnets are the same. Magnets either stick to each other or repel each other because of the interaction of their fields. So gravity is the first field you look at in Physics 11. Physics 12 is where we save electrostatics and magnetism. So to help explain how two bodies that are not in contact can exert a force on one another, we use this idea of fields. Fields are spheres of influence. They're invisible, intangible. They simply demonstrate how strong a characteristic is at a certain distance away from a particular object. I mean, the example that I give you guys here is the idea of a campfire, having a heat field. You can feel the effects of a fire without actually feeling the fire itself, and as you get closer, obviously it gets warmer. As you get further away, obviously you're going to get cooled down. Gravity is the same kind of idea. And actually, this is what we're going to put in here. The closer we get to the field, that's a hard one to see. The closer we get to the fire, the stronger the field becomes. Likewise, the larger the fire is, the stronger that heat field is. If you've never experienced a good bonfire, this is something you absolutely must do at some point. Buddies of mine and I met. I have a buddy who's got a big field. We put a fire out back. It was a New Year's Eve. We spent like 2 weeks gathering pallets, and we had a bonfire in his backyard to the point where the house was several hundred meters away, and we started to melt the siding on the side of his head. The large fire produced quite the heat field. It was New Year's. It was January 1st. And we did not need jackets outside. It was so warm. But I digress. Gravitational fields are defined as the following. They are defined as the strength of gravity created by a mass at some point. And that point is allowed to change. So the gravity field is going to be stronger or weaker at different points in space around an object. And for gravitational field, it is a 3D shell around an object. So if you take a look at these two formulations we had for gravity, we had this one here, Fg equals mg was the first one we looked at. We said that g was the acceleration due to gravity at or near the Earth's surface, and then universal gravitation took over and said, okay, well, this is going to give you the gravitational strength anywhere. These two are very closely related. This m here and this m here represent the same mass. And so what that means is that this piece here, this gm over r squared, and this little g here, if these two m's are equal, then at or near the Earth's surface, these two expressions need to be equal. So this little g doesn't just represent 9.81 anymore. It represents the gravitational field strength anywhere. So what we're going to do now is we're going to equate this little g to big G times big M over R squared. And the units on this thing, when we first gave you little g, we said that the units on this thing were meters per second squared. This thing over here is actually also equal to Fg over m. This thing is in newtons per kilogram. And so, like I've said it once already, I'll say it again. This little g here, measured in meters per second squared, is also equal to a newton per kilogram. So for every kilogram of mass that some other object has, it's going to experience 1 newton or a newton of force, is what this means. So this here is what we call gravitational field strength. So I'll do a couple examples of what I mean here. So I said it yesterday, the Earth is not actually a perfect sphere. Just like a spinning basketball isn't actually a perfect sphere either. As soon as you start to spin something, the inertia of the object in the plane that it's spinning in is going to cause the mass to try and fly away from the center of that object. So if you spin a basketball this way, and it's spinning parallel to the ground, it's going to get chubbier around the equator. If for whatever reason you spin it vertically, and it's spinning this way, perpendicular to the ground, it's going to get fatter on the poles. So because our Earth is rotating around the equator, tilted, but around the equator, it gets bulgy in the middle. So because of that, the radius of the Earth isn't constant. It's actually different between the poles and the center of the Earth than it is from the center to the equator. Yes, here, Dave. Sorry? Like a yoga ball? What do you mean? Yes, but it's not I don't want you to get confused with why it's not a perfect sphere. If somehow we were to stop the Earth spinning, it would sphere up. It wouldn't be squishy like a yoga ball just is anyway. So a yoga ball is actually, so the effect there is different. A yoga ball is actually kind of compressed around its own lack of interior air pressure. So I want to use the basketball as an example. A pumped up basketball is going to be as close to a rigid sphere as you're going to get from a ball in the gym. Spinning it is what's going to cause it to pudge out. Do you understand the difference? So the acceleration due to gravity is going to be different at the North Pole versus at the equator. It's not going to be different enough for you to notice it. It's not like you're going to go to the equator and you're going to start jumping. You're like, oh, I'm falling slower. Like it's not going to, the effect isn't that big. And we're going to calculate right now what the effects are. So the acceleration due to gravity, or another way to put this, acceleration due to gravity is now also called gravitational field strength. Those are now one and the same. At the North Pole can be found like this. This is the radius of the Earth at the North Pole. So to find the gravitational field strength or the acceleration due to gravity, we're not going to use Fg equals gmm over r squared anymore. We're just going to use this portion of the expression here. Little g equals big G times big M over r squared. Again, you don't need to memorize this. It's on your formula sheet. So G equals little g, gravitational field strength, is equal to the universal gravitational constant times the mass creating the gravity divided by where you are in space away from the center of the mass creating the gravity squared. So this is going to be 6.67 times 10 to the negative 11 times, and it's the Earth. Earth's mass is 5.98 times 10 to the 24. You don't have to memorize that. It's on your formula sheet. Divided by r squared. Now, r at the North Pole is 6,370,000. For the sake of punching this into a calculator, I'm going to get rid of scientific notation here. Squared. I've done the calculation for you here. At this location, this value, gravitational field strength, or the acceleration due to gravity, is actually 9.83 meters per second squared. So slightly higher than what we've been using up to this point. Not a lot, like it's 2/100ths different, but calculatable, and given the right equipment, noticeable in a lab. At the equator, let's take a look at it. At the equator, do you think this should be bigger? The number's going to be bigger or smaller? At the equator, you're further away. So because this number is bigger, this is going to be bigger. What do you think should happen with the value for gravitational field strength? Should get smaller. If the denominator of the fraction is getting bigger, the value should be getting smaller. So let's go figure that out. We're still going to use G equals gm over r squared. 6.67 times 10 to the negative 11. It's still the mass of the Earth. 5.98 times 10 to the 24. All over. Now this is a slightly larger number. 6386000 squared. Which is, I mean, it's 16,000 meters. That's not an insignificant difference. But when compared to the size of the rest of the Earth, 16,000 meters doesn't really seem like a lot. What do you get for the value for the acceleration due to gravity at the equator? One could argue that the buildings, like nothing that's on our Earth, except for a few small meteorites, well, and some really big ones, but nothing on our planet now is made from something that wasn't here already. So just, that's what I'm trying to answer your question. So like the buildings and stuff don't change the overall mass of the Earth because we made them from things that were already here. We just moved it around. We just took existing Earth mass and put it somewhere else, reconfigured it. I mean, you're the same. Your physical body is made up of phosphorus, nitrogen, carbon, oxygen, hydrogen, if I didn't say it already. Did I say potassium? I don't know. You've got iron, minerals, various minerals, calcium's in your bones, and all of that came from the food that the woman who birthed you consumed over the course of her pregnancy. And that just came from stuff we planted in the ground. So everything that's here already, people, buildings, is just a reconfiguration of the stuff that was already here. So this number accounts for all of that. Yep, it's all part of that. The only way this number changes is as we go out and if we start mining asteroids or if we decide to mine the moon and then start bringing that crap back. That is how this number is going to change. Otherwise, it's just moving around what's already here. Good question. That'll have a whole bunch of other interesting effects if we start to jack this number up too big by bringing other stuff here. There's a whole host of other problems. What'd you get? I saw a bunch of you working on your calculator. 9.78. So again, not abundantly different from the value we have been used to. Like this is still, when you guys were calculating it using the Spark tape a couple weeks ago now, this is still well within experimental error, plus or minus 10%. But the effect is there. With careful enough measurements, with precise enough lab equipment, you could determine the difference here, and you could witness things experiencing this difference. It wouldn't look like a lot to you, but it exists. The difference exists. The one assumption we're making here is that this M is universally distributed throughout the Earth, and that's just not true. For example, in Denver, Colorado, and that's just one location that I know about. There's others around the world, but the density of the Earth is such that the gravitational field in Denver is greater than other equivalent altitudes around the Earth. Just because of what Denver is built on, it's denser. And so more of the Earth's mass is located in certain pockets. And so you're going to get different gravitational field strengths depending on what's in the ground you're standing on. Again, the effect isn't huge, but it's noticeable. It's measurable. So the assumption here is that this mass is universally distributed. It's not. But we get this effect. So we've talked about the moon a lot. Let's look at the moon. The moon is 385,000 kilometers away from the Earth's surface, so 385 million meters away from the Earth's surface. What is the gravitational field strength at this distance? So you've got the Earth. There's the center of the Earth. Somewhere way the heck out here, you've got a moon. The moon is bigger than we think. The moon is actually similar in size to the planet Mars, which is weird to think about. And it's fairly far away. It's actually exactly far away enough that you could line up all of the other planets between Earth and the moon, and they would fit in there quite comfortably. It's pretty far away. And when we talk about this, the moon is this far away. What we're talking about is the center of the moon. So we don't actually need the moon's radius for this. We're not talking center to center. If the moon is this far away from the Earth's surface, what we're talking about is the center of the moon to the surface of the Earth. So the altitude of the moon, you could word it a different way. The altitude of the moon is 385,000 kilometers. So this number in here is 385,000. And because we're given this value here. The radius of the Earth is quoted to us in meters. I'm going to put this into meters as well. To convert from kilometers to meters, we just multiply by 1,000, which is just going to tack on 3 more zeros. 385 million meters. Now, the radius of the Earth is 6.38 times 10 to the 6, or 638,000. Radius of the Earth, 6 million meters. Altitude of the moon, 385 million meters. Really far away. To find the gravitational field strength out here where the moon is, we're going to use little g equals gm over r squared. It's going to be 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 divided by the sum of these two. So that's going to be 391,380,000. What is that value? What do you get? Those of you who are punching your calculator, what's the value? 2.60 times 10 to the negative 3. So 0.0026. And that is meters per second squared. So that's really small. The acceleration due to gravity out where the moon is 0.0026 meters per second squared. So what that means is you take away the moon, if you were placed there in space, every second, your speed towards the Earth would increase by 0.0026 meters per second, or another way to think about it, your speed would be in like the 2.5 millimeters per second range. It'd be very small. So then flip the page. Given all of this information, and given the mass of the Earth and the mass of the moon, even though that g value is really small, let's calculate the force between the Earth and the moon. We want the force of gravity. We don't need to use universal gravitation this time. We can use Fg equals mg because we know this value. This g is gravitational field strength. And we know this value. We just calculated it. This value, where the moon is out in space, is equal to 0.0026 at the moon. So then all we've got to do is to find the force of gravity, we take the mass of the moon, 7.36 times 10 to the 22, not an insignificant rock orbiting our planet, and we're going to multiply that by 0.0026. The gravitational field strength out where the moon is. What's this value? What is the force of gravity on the moon from the Earth? Oh, and actually vice versa. What would you get? .91 times 10 to the 20. And that's measured in newtons. That's force. So to put that into perspective, that's 191 followed by 3, 6, 9, 12, 15, 18 zeros. 1, 2, 3, 4, 5, 6, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 zeros. That is the force of gravity on the moon from Earth. That is very large. So why then does the moon not slam into our planet? You've got the Earth right here. You've got the moon out here. The force on the Earth, the force on the moon from the Earth is really big. Fg equals 1.91 times 10 to the 20. And it doesn't matter where in space, in its orbit, the moon happens to be, it's going to be experiencing that same force the whole time. So why doesn't the moon slam into our planet? Yeah, Lena. Because it's already doing this. If you were to stop the moon somehow in its orbit, it would slam into the planet. It would be awful. Everyone would die. But that's what would happen. So the reason that it doesn't, Lena, you're absolutely correct, is because the moon is already moving. So the moon, it's in orbit is the language we use around the Earth. But what is an orbit? An orbit is an object that is constantly trying to fall to the Earth, but it is constantly missing. Yeah, kind of. The object in orbit has some velocity. It's got its own inertia. It's trying to fall to the surface, but it just keeps missing because of its motion that's perpendicular in every case around the path. The motion is always perpendicular to the direction of the force on that object. And this is what every orbit is. Yes, here today. Is that true? Look. The moon is moving away from the Earth at a rate of about 3.5 centimeters per year. Why is that happening? Well, according to what I just searched online. Oh, interesting. This is weird. Okay, let's see if I can explain this. There's a piece of physics you're missing because it's too hard for you at this stage. But objects that rotate have energy. There's different kinds of energy an object can have. Rotational energy, kinetic energy, so just the energy of a moving object. And the explanation seems to be that the tides on our planet, that the moon creates these tides, creates bulges around the Earth's rotation. And this rotational energy in the Earth, because of how the gravity changes when the oceans slosh around, actually provides the moon with more rotational energy. How that happens is complicated. Don't worry about it. The answer to your question is that's what's going on. So because it gains, sorry, and it's not rotational energy, it's velocity, it's orbital, it's kinetic energy, it's orbital energy. So as the moon is speeding up this way, it is actually free to gain orbital radius. The faster the object's moving, it can now elevate itself to a higher orbit. There is a maximum distance that this will happen. And apparently, that will happen in about 15 billion years. I'm going to calculate here. 15 billion. 2, 3, 4, 5, 6, 7, 8, 9 times 3.5 centimeters, 0.0. Divided by 100. It's actually going to get about 5,670 kilometers further away in about 15 billion years. Assuming nothing else happens between now and then, which is a pretty big event scheduled sooner than that. At some point, the sun is going to expand and vaporize all of us and everything out to past Mars. I don't know if the moon will even be here then. So and the time scales are just ridiculous at that point. So I don't actually know if I answered your question, but that's kind of what's going on. It's not an urgent problem. The effects are not going to be noticeable for many, many lifetimes. But you're right, it's still a thing. So every orbit, going back to this, every orbit is just an object that's trying to get back to Earth that's constantly missing. Every satellite, every astronaut, every space shuttle, every rocket, everything is up there trying to hit the Earth's surface and it just can't. There's a flip side to this. What this means is that every object that is successfully able to fall back to the Earth's surface just hasn't been given enough energy yet to miss. So if you throw a football at different speeds, it will travel forwards, but eventually it will fall back to the ground. Yes? If you've ever thrown a ball, you've experienced this. If you're weak, it goes like this. If you're slightly stronger, it goes like this. Well, not quite like that. It's more parabolic, as we've experienced. But, as perhaps you've seen in various cartoons, if you throw it hard enough, you could actually get this thing to fly, and again, assuming there's nothing in your way, various mountain ranges, trees, etc. If you could throw the football hard enough, you could get it to orbit its way around the Earth, which would be terrifying and awesome. So we're standing at the top of a very high mountain, ignoring friction, and you just happen to have your trusty football cannon. You could shoot it at some velocity. First, it would probably fall, but as you increase the velocity enough, you could get it to the point where instead of falling back to the Earth's surface, you're actually able to orbit that football around the planet. This velocity, the velocity required for this to happen, is called the escape velocity. And this is going to get saved for Physics 12. There's a unit in Physics 12. It's one of the last ones you'll do before electrostatics and magnetism, called circular motion, and it's actually quite complicated. Well, it's more complicated than the stuff that we've looked at so far, but it's really fascinating. Yes, here, Day. Yeah, Germany was trying to do this during World War II. Yeah. So it's theoretically possible. The physics is sound. It's doable, but it's wildly complicated because this is something. This is an assumption that we're making here. These speeds are sufficiently high enough that this becomes a massive problem in the real world. This is why space shuttles have heat shields. Rockets need to be built to withstand the heat. You can't just launch anything. Like the football would disintegrate well before, because of the air friction, just because the air would tear it apart, which is not something we normally have to deal with. Unless, has anyone ever received a wind burn? Wind burn is a thing you experience in skiing. The combination of the cold and the wind rushing past you causes your skin to burn. That's the very beginnings of something of an effect like this. We're going to ignore these boxes down here. Don't worry about it. So that is all I've got for you for gravitational field strength for today. We're not going to do that thing either. What I'd like you to take a look at are these questions here. I want you to do them all. There are some values you're going to need off your formula sheet, because it asks you for things like the weight of an object near the surface of the moon. So either you remember what the acceleration due to gravity is, or the gravitational field strength is at the moon, or you head to your formula sheet and you find it. But now we can start to leave our planet and start to talk about some of these other things. You can look at the acceleration due to gravity on the surface of the sun. So I want you to take a look at these 8 questions.